In this calculation for N5 Electrotechnics, we'll be looking at speed control for DC motors. Now, having a look at this formula, you'll notice that the speed is directly proportional to the EMF. However, it is inversely proportional to the flux. Now, if you want to increase the speed for a DC machine, you either have to increase the EMF or decrease the flux. And alternatively, if you want to decrease the speed, you need to decrease the EMF or increase the flux. Now here we have a circuit diagram for a series motor and a shunt motor, and these would be considered to be your original circuit diagrams. In the original condition, the motor is running at normal speed and full torque. Now if you want to increase the speed, you will have to take a diverter resistor, and for a series motor you would put the diverter resistor in parallel with the field winding, and for a shunt motor you would put the diverter resistor in series with the field winding. After the speed has changed, current from the supply will change. That is, the supply current IL1 will change to IL2. The speed will also change from N1 to N2, and the induced EMF changes from EMF1 to EMF2, and the torque also changes from torque 1 to torque 2. However, the terminal voltage and field resistance will remain the same from the original circuit to the diverter circuit. Now, if you want to decrease the speed for a series motor and shunt motor, you will do the same thing. You will put a diverter resistor in series with the armature. So when answering questions on speed control, make sure you always draw the original circuit and the circuit with the divider. Our main speed control formula is E1 over E2, which is equal to N1 times the field current number 1 over N2 times the secondary field current. And we are assuming that the flux is directly proportional to the field current for both speeds. Our other formula that we could potentially use, we won't use it in this example, but just in the future reference, if you have a diverter resistance placed in parallel with the field winding, we have our secondary supply current coming into the parallel branch. We have our secondary field current passing through the field resistor, and then we have our secondary armature current. So for the current divider rule, to calculate the secondary field current, it will be IA2 times the diverter resistance over the diverter resistance times the field resistance. And we'll take a look at this formula in some other examples. Now, for illustration purposes, when we have torque, you'll see in each question they give us different information. So just to give you some background before we start our first example, if the torque is unaltered, torque 1 is equal to torque 2. If the torque is halved, it means that T2 is going to be equal to 0.5 times T1. If the torque is reduced by 30%, it means 100% minus 30% gives you 70%. So this implies that T2 is equal to 0.7 times T1. And then if you are given a 25% speed reduction, 100% minus 25% gives you 75%. So therefore N2 will be equal to 0.75 times N1. Alright, that's the background. Let's take a look at our first example. Example 1.10 on page 38. A shunt-wound DC motor draws 30 amperes from a 250 volt supply. The resistances of the armature and shunt field windings are 0.2 ohms and 150 ohms respectively. The full load speed of the motor is 950 revs per minute. There is a 30% torque reduction when a 1.2 ohm resistor is connected in series with the armature. Calculate the new speed of the motor, assuming the field coils are unsaturated. So, very important, the question is asking to calculate the new speed. So we're going to be looking for N2. And just a reminder, when you put a resistor in series with the armature, it means that we are trying to decrease the speed of the DC machine. Ultimately, by decreasing the speed, it means that your secondary EMF will be a smaller value and your secondary speed will be a smaller value. Just something to keep in mind to check your answers when you do your calculation. Right, so here's my original circuit. It's a shunt motor, and then we have our diverter circuit where we place the diverter resistor in series with the armature. Let's take a look at all the values that are given. We have a supply current of 30 amperes being drawn by the armature assembly. We have a terminal voltage of 250 volts. Our original speed is 950 revs per minute. Our shunt field resistance is 150 ohms, and our armature resistance is 0.2 ohms. Now, just a note, they said that the torque is reduced by 30%. So to calculate the secondary torque, it is 0.7 times T1. And we say that because it's unsaturated, we assume that the flux is directly proportional to the field current. Now, in our second circuit, the supply current is going to change, the armature current is going to change, the EMF will change, and the speed will change, and the value of the diverter resistance in series with the armature is 1.2 ohms. Right, so to solve this problem, we use this equation, E1 over E2 is equal to N1 times the primary field current divided by N2 times the secondary field current. So the question is to calculate the secondary speed. So we manipulate the equation, and this is how we're going to solve the problem. But if you take a look over here, this means we need to calculate E2, we need to calculate E1, we need to calculate the primary field current, and we need to calculate the secondary field current. Now, your EMF equation for a shunt motor, E is equal to V minus IA times RA. Just a note there. And to calculate IA, one of the ways to do that, IA is equal to IL minus I shunt. Okay, you remember that from our previous examples. Right, so the first thing we're going to do is to calculate the field current. So the primary side is going to be V over R shunt, and to calculate the secondary field current, it is V over R shunt. Remember, voltage stays the same in parallel, so the terminal voltage is 250 volts, the shunt resistance is 150 ohms, and we get a field current of 1.667 amperes. And our secondary field current, well, it's the same voltage of 250 volts, the same shunt resistance, the field resistance of 150 ohms. So we end up with 1.667 amperes. Right, the next step now is to calculate EMF1. So to calculate the primary EMF generated by the armature assembly, it's going to be V minus IARA, because it's a shunt motor. The terminal voltage is 250 volts. Now, here we have to calculate IA. The armature resistance is 0.2 ohms. So to solve for EMF1, right, so to calculate IA1, it's going to be IL1 minus I shunt 1, okay, which is basically your field current. Your supply current on your primary diagram, your first supply current is 30 amperes, and your field current on the primary side was 1.667 amperes, and that's basically the same as I shunt. So therefore, the primary armature current is 28.333 amperes. Right, we can substitute that in here. 28.33, always round off to 3 decimal places. So therefore, EMF1 is 240.333 volts. Remember, EMF1 will be bigger, EMF2 will be smaller because we're decreasing the speed. Right, now to calculate EMF2, and we have a little bit of a problem over here because we do not know what the secondary supply current is. So therefore, IA2 is unknown because the secondary supply current will change. However, we know that the flux is proportional to torque, and we can use the torque formula to find IA 2. Right, so let me first write down the equation for EMF 2. It is V minus IA2 times RA. And unfortunately, to calculate IA2, we're going to use the torque formula. T1 over T2 is equal to IA1 times R field 1 over IA2 times R field 2. Right, let's substitute those values. Now, although we don't have the actual values for T1 and T2, we know that T1 is equal to 0.7 times, so therefore T2 will be 0.7 times T1. Remember, it's reduced by 30%. IA1 is 28,333. I field 1 is 1,667. And we do not know what IA2 is. And R field 2 is also 1,667. So just doing a little bit of mathematics here, we can cancel out the common factors. Cancel out T1 and T1. So therefore, IA2 will be 28,33 amperes multiplied by 0.7, and that will give us 19,833 amperes. Right, now that we've got IA2, we can work out the secondary EMF. Remember, EMF 2 should be smaller. It's 250 volts minus 19,833 times the armature resistance of 0.2. Right, so the secondary EMF works out to 222,234 volts. Right, now we can actually answer the question by calculating the secondary speed. And I showed you earlier that formula. It is E2 times N1 times the primary field current over EMF 1 times the secondary field current. So let's substitute everything in there. The secondary EMF was 222,234. The primary speed was 950 revs per minute. The primary field current was 1,667. And EMF 1 is the bigger one. It's 244,333. And the secondary field current is exactly the same, 1,667. Therefore, the secondary speed should be reduced to 864,076 revs per minute. Right, thanks guys for watching this video for DC speed control.